In the previous topic, we have discussed some basic concepts of computer. What are the functions of computer? What are the operations of a microprocessor? How it performs? What is the meaning of fetch? So on, etc. As already discussed, we shall now discuss about the basic concepts. So we have discussed that there are two important things to understand the subject called as computer organization. One is the number systems. What is the data the computer understands? In which form the computer understands? That is binary. Similarly, the concept of memory, because the processor doesn't contain any instructions within itself. Everything should be brought from memory. So first of all, we should know what this memory is, how it contains the instructions, data, so on, etc. So the whole language of a computer is in the binary form, which is easy to represent, that is ones and zeros. Anything can be represented in the form of this binary data called as ones and zeros. Language plays very important role if you look at in human perspective also. For example, say that I belong to some southern part of India. If I travel to northern part of India, definitely if I know the Hindi, I'll be more comfortable to speak or communicate with the people. Or else I'll fall into trouble sometimes. In the same way, if a person belongs to northern part of India, if he goes to southern part of India, if he knows that particular language, it will be more comfortable for him. So it means that language plays very important role in human perspective also. In the same way, the computer understands only binary language. If you want to communicate with the computer, if you want to design the internal structure of a computer, you should also, or in other words, we should also know how the data can be represented. So this topic will help you to understand how the ALU operations are performed, how the instructions data are represented in the binary form. So the number system, even though it's a basic concept, it's very important to understand, because you know that the whole structure of a building is based on how strong it is built on the foundation. So these are all basic things. Now we shall discuss how actually this number systems can be understood. By the way, you have already covered the number system topic in digital electronics. You might have studied in the digital electronics. I am not going to discuss in the same orientation. I will be discussing the number system with computer organization point of view, so that you can solve the problems in very simpler way. Fine. So there are different kinds of number systems. For example, say you know the decimal number system, octal number system, binary number system, and the other one is hexadecimal number system. So in all these cases, we can understand how the data can be represented. So let me take this octal number system. Fine. So these all words called as deci, octa, binary, hexa, they belong to Greek and Latin words. So what is the meaning of deci? So deci indicates 10. It means there are 10 digits in this number system. The same thing I am calling it as base. For example, the base in this is 10. The same way in octal, the base is 8. In the same way, the base is 2, and here the base is 16. Fine. So in decimal number system, we are habituated to calculate or solve the problems from childhood. So your brain is very clearly tuned to the decimal system. But however, if you go with the other type of number system, you have to think little bit, right? So in decimal system, there are 10 quantities. Say there are 10 quantities. Say the values are 0 to 9. So 0 to 9 are 10 values. After 9, there is no new value. So we write the initial value 0 and take it as 1. So this is what actually we are calling it as 10. 10 is actually not a new number. It's not a new digit. After 9, there is no next value. So we start again with 0 and 1 carry. It goes on increasing, so on, etc. till 19. And after again 19, again 9, it comes 0, 1 carry, it has become 2. That is how we got this decimal system. Come to the octal system. So here the base is 8. It means how many values are there? How many quantities? 8 quantities. 0 to 7. The rule is same for any kind of number system. Here there are 8 quantities, 0 to 7. The next value here is also 1 0. But be careful, this 1 0 is not 10 as we represent in the decimal system. The value of this 1 0 equivalent in decimal is a bit different. So 1 0 is in octal. If you compare with the decimal, it is something like 8. So we have to represent these values with respect to decimal, because we understand the decimal numbers very clearly. We are habituated to it. Fine. Let us go further. Take the other one called as binary. In binary, there are only 2 quantities, that is 0, 1. Here also the next value is 1, 0 only. Similarly, hexadecimal. Hexadecimal base is 16. There are 16 quantities. Here 0 to 9 is same, but after 9 it's not 10, it's something different. For example, say I am considering 0 to 9. After that it is A, B, C. Okay, it is A, B and C, D, E, F. After F, the next value is 1, 0 here also. Now, by looking at this data, are you not getting confused? In all these number systems, there is a quantity called as 1, 0. But this 1, 0 should be called as 10 only in the decimal system. So it's not in other type of number system. For example, if you consider this 10, let us say, it is only in the decimal system, not in other systems. So in the decimal system only, this is 10. But what is the base here? 10. In this case, this 1, 0 is not 10, the base is 8 here, octal. Here the base is 2. Here the base is 16. So in other words, we can represent hexadecimal numbers as H. That is why, as per the rule, if you understand carefully, let us consider like this. So for example, I am considering this. Okay, let me take out this one so that you'll understand easily. So if you observe carefully, here, to make it clear, this H is indicating that 1, 0 in the hexadecimal. As per the rule, decimal number should also be denoted as D. Octal should be, binary should be denoted as some B. Octal should be O. But from childhood, we are habituated, so we don't bother about this D or this O or this binary. Are you able to follow? Right. But in case of representing the numbers, definitely you must write the base, or else the problem will go wrong. Fine. So here, come to the point. In all these number systems, you find 1, 0, which is equivalent to different values when compared with the decimal system. We are more flexible with the decimal system, so let us compare the remaining number system with the decimal system. Now, for example, let us consider like this. Say, now I am comparing these numbers with the decimal system. I am comparing the octal with the decimal system. I am just writing as D. So 0 to 7 story is same. But after this, the next value in the octal is 1, 0, but the next value in the decimal is 8, because there are 2 more values in the decimal system. And hence, that is why we say the decimal equivalent of the octal value 1, 0 is 8. It goes on continuing. For example, say you want to write this as 1, 1. How long it will go like this? 1, 1, 1, 2, so on, etc. till 1, 7 only. The next value will be 2, 0. But remember, these are our octal quantities, not decimal quantities. If you compare this value with the decimal now, what are these values now? This will indicate 9, 10, so on, etc. So after this quantity, every value in decimal is 2 less than the octal value. So this value will be 15. The decimal. So this is not decimal, this is octal quantity. Then the next value, this is 20, it will be go on, so on, continuing. That is about the comparison of octal and decimal. Now, compare the binary and decimal. So, 0101 same concept, but the next value in the decimal is 2, but the next value here is 10, but it is a binary quantity and this one is a decimal quantity. So, it goes on increasing. For example, say next value will be 1, 1, next value will be, here maximum value is only 1. So, this value is 3 here, it is a binary quantity. The next value will be 1, 0, 0. So, this is binary, this will be 4. So, it goes on continuing. So, that is how we can write the equivalent values. I am just removing it so that you can easily understand. Okay, fine. So, this is the decimal quantity. Okay. This is the decimal quantity. Fine. So, it goes on continuing. Similarly, now let us compare the hexadecimal values with the decimal values. How to do this? Let us discuss now. I'll just increase the font. Okay. So, this is decimal and hexadecimal. Very easy. From 0 to 9 concept is same. But after 9, the next values in the hexadecimal are A, B, C, D, so on, etc. But the next value in the decimal is 10. So, A stands for 10 in decimal. This is 11. This is 12. This is 13. This is 14. This is 15. And 10H stands for 16 in the decimal. But to solve the problems, you should also know till 20. I mean to say that, for example, say it is 10H. So, after 10H, the next values are like 11H, 12H, 13H, 14H. At least you must know till 20. It means if I compare these values, 11H stands for 17 in decimal, 18, 19 and this is 20. So, this is how we can write the representation of different number systems in the decimal form. Why is it required? We will discuss in the further data. Fine. So, you should very clearly understand how we have compared to these values. Okay, right. Okay. Not only this, you should also know how to represent the hexadecimal numbers in the binary form. Okay. So, how to do that? So, at least you should know till 20. But by the way, you know in the gate like calculators are used, you can easily convert, no problem. But when you go for some competitive exams like PSUs and all, most of the cases the calculators are not allowed. Then how to solve the problem in a simpler way at the same time in the less time? How to solve it in the less time or quickly? We shall see some points to be noted, right? You should know how to solve the data in this number system. Fine. Now observe carefully. We will also write what is the binary equivalent of this data. For example, I want to find out what's a binary equivalent and all. Let us discuss now how to write this data in the binary form. So, you should be very flexible to convert from one number system to the other number system. How to write in the binary also you should know clearly. Fine, we will see the conversions one by one. For example, let us consider the hexadecimal numbers and binary. So, tell me, binary is just a game of two. If you know this language of binary, I can easily assure you that this subject will be very simply a cakewalk for you. That is why I am concentrating more on the basic fundamentals. So, binary 2 is the base. So, if I want to represent 16 quantities, binary is just coding, you can easily understand. Anything can be coded in the binary form. So, if I want 16 codes, hexadecimal 16 values are there. Now, how many bits are required? 4 bits are required. It means to represent 16 quantities, I have to generate or provide 16 codes. To have 16 codes, 4 bits are required. That is why we are considering the 4-bit value to represent the hexadecimal numbers. It means, for example, say that, so this is hexadecimal. So I am taking 4-bit positions, right? So as a power of 2, if I consider, this is 2 power 0, 2 power 1, 2 square and 2 cube. If I write the weights of this is 8421. Sometimes it's also called as 8421 coding, right? Now observe carefully. So here I want to just emphasize on how to write this data in the binary form. Okay. Now we want to represent the hexadecimal numbers in the binary also. It means let us start from, say, I want to write from 0. Okay. So let us say I am writing from 0h. So how do you write this 0h in the binary form? So weight is simply 0, all zeros, 0, 0, 0, 0. Right. 1h. What is 1h? It is simply position of 1 here, which is 1 and put all zeros. Right. So on, etc. 9. How do you write 9? 9 is simply 8 plus 1. So we simply write 1, 0, 0, 1, because the binary digit and its weight must be multiplied to have the magnitude. Therefore, we write like this. So let us say A. Actually, A should also have H. To avoid the confusion in alphabets, I am simply writing only A. To be frank, you must write AH. But whenever you write a hexadecimal number which starts with alphabet like A to F, you must put 0 before it. It means I can write 0AH. I can write as 0AH. Or to avoid the confusion, I am simply putting A as of now so that you can understand the calculation easy. So A is 10, 10 means 8 plus 2, 1, 0, 1, 0. B stands for 11, 1, 0, 1, 1. C is 12, 1, 1, 0, 0. D is 13, 1, 1, 0, 1. E is 14, this is 1, 1, 1, 0. And F stands for 15. Say, I am writing here, F stands for 15. This is 1, 1, 1, 1. This is how we write the codes of all the 16 hexadecimal values. Okay. Now, to perform these arithmetic operations or logical operations, you must be well acquainted with the concept of binary conversions or how to write the data in the binary form. So, initially, we will solve some simple questions how to convert the data from decimal number system to any other number system. How to convert decimal value to other number system. We will solve some simple questions. Later on, I will discuss the problems. But I tell you, don't feel that already we know this, but basics are very important to be strong to solve the rest of questions. Fine. So now let us learn how to represent a decimal value in any kind of number system. So I am writing here decimal number system to other number system. So what is the technique of converting this? So to convert decimal value to any other number system, you have to divide whatever the decimal value, you have to divide the number with the base of required number system. Whatever the base you want to convert, you have to divide the decimal number with the base of required number system. And when you get the reminders, take the reminders from last to first. So how to convert decimal value to other system? The method is divide the value, whichever you want to convert decimal value, with the base of required number system, then consider the reminders from last to first. Let us take an example. I want to convert, say, a value 14 decimal to binary. So very simple, divide the number with the required base. So whatever the base you require, you have to divide with that. So the number is 14 in decimal, base is 10. I need to have in binary, so 2. Just go on dividing 14 by 2. So 2 7s 14, remainder is 0, 2 3s, remainder is 1, 2 1s, remainder is 1. It means second step is consider all the reminders from last to first. So you get a value called as 1110, 1110. So this is how we convert from decimal number system to other number system. If I want to convert the data back to the decimal again, so this is the binary value. You can take the weight 8 plus 4 plus 2, that is 14. Now again I want to convert this data back to the decimal value. Very easy. For converting decimal to others, we have to divide. From other system to the decimal system, we have to multiply. That's all. Multiply with the weights. Now take this value, for example 0. 0 into what is the weight? 2 power 0 plus, okay, plus this 1 into 2 power 1 plus this 1 into 2 square plus this value, whatever the data it is. I'm just removing. Okay, so this 1 into 2 cube. So you get this value as, this is 8 plus 4 plus 2 plus 0. So again, if you add all these things, you'll get again 14. So this is how we can convert from decimal to other system by simply dividing and considering the remainders. Similarly, back to the decimal from binary, you have to multiply the digits with the corresponding weights. This is how we can convert from the decimal to other system. For example, to make it clear, let me take one more problem. Say, I want to now convert some decimal number to hex or hexadecimal. So how to do that? Let us consider now. Let us consider this value, how to solve this data. Fine, decimal to hexadecimal. Let us consider like this. Say, I have a decimal value called as say 25. I want to convert this decimal value to the hexadecimal. Very simple. How do we do this? Divide 25 with the required base 16. So how much it is? 16 ones, and what is the remainder? 9. Remainder is 9. It means you cannot go for the 19. So here it is 19, or in other words we can write 19H. 19H. Right. That is how we can convert from one number system. For your understanding, I am taking other value. Say I am taking a value 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0. This is the binary data. I am just recapping the points. So this data I want to write in hexadecimal, let us say. What is the quantity? Now tell me, what is the relation between hexadecimal and binary? What is that? 1 hexadecimal digit is equals to 4 binary bits. Therefore, we have to take group of 4 bits. So in the previous topic I have discussed, what is the meaning of group of 4 bits? Called as nibble. So we take 1 hexadecimal digit as a nibble. Okay. Now continue the point. Let us take the next one. So here I am grouping the values as 1, 2, 3 and 4. It's a just number game. If you can solve this, it's very easy to follow. Okay, tell me what is this value? It is 2. It is very simple, 8421 coding, 4 plus 2, this is 6, this is 9 and this one is 7. So we can write this value as 7962, or in other words 7962H. Always remember, don't forget to put H for the hexadecimal number. If you forget, the data will go wrong. Fine. That is how we can write from decimal to other system or other system back to the decimal. For example, for your practice, I am giving you a couple of problems. Say I am writing a value. Tell me how many bits of data is this? If you observe, how many bits of data? For the 16 bits data, right? 16 bits data means how many bytes? 2 bytes. Or how many nibbles? 4 nibbles. You must be very flexible to represent the data in the form of bits, nibble, byte. Sometimes you may call it as word also based on the processor. We'll discuss that concept later. Okay. Now I want you to write this data in the binary. How do you write? This data I want to write in the binary. Very simple. 8. What is 8? 1 0 0 0. 5 is 0 1 0 1. So this is how I can write this data in the binary form. In the digital electronics topic, you might have discussed or you will be discussed based on the subject, whatever you have covered. This all data. How to convert from one system to other. I am not going to discuss the whole topic here. I am discussing whichever is required with respect to the subject called as computer organization. Okay, fine. So like this, we can solve the data in a simpler way. I want you to practice this number systems as much as possible so that your speed of solving the question improves a lot. Fine. Okay. Let us go further. How to perform simple additions. Now, I think you are well aware of converting from one number system to other number system. Let me give you one more question. Say this is example 1. Say I am giving you one more question. Now, if you have solved, try to understand 0 0 1 1 1 0 0 0 0 1 1 1 0 0 0 1. Okay, this is just a test for you. Okay, I want you to solve this question within half minute. Within half minute. Can you try it? Yes. You stop the video and solve the question within a half minute. Okay, so I want you to assess yourself. Then it will be easy to solve the problems quickly. Time plays very important role in the competitive exam. So more fast you are, more marks you can gain. So that is very important parameter in the competitive exams. Right. So what is this value? How much you got? I want this number to be written in the hexadecimal, or you try to solve in the octal form. So if you have done in hexadecimal, try to solve in the octal. How do you solve in octal now? Now tell me, what is the relation between octal and binary? How many quantities are there in octal? Let me ask you, octal how many quantities are there? 8. If I want to code anything in the binary, it should be power of 2. So 8 can be written as 2 cube. It means I require 3 bit positions to write this 8 codes. It's very easy, just coding. Everything can be represented in the binary form. So it means now I should take group of 3 3-bits each. So 1, this 2, this 3, another 3, another 3. When there are no values, you can just put 2 more zeros. So what is the equivalent value you obtain now? What is the value you obtain now? What is this value? 1. This is 6. This is 1, 4, 3, 0. It means that 34161. So this value is equals to 34161 in the octal. So this is 001, 110 is 6, 001 again, 1004, 3 and 0. Like this, you should be flexible enough to convert from one number system to the other number system. Hope you have understood the data. Right. In the computer, most of the cases, the data has to be performed with some arithmetic and logical operations. Like arithmetic operations you know very well, addition, subtraction, multiply, division, increment and also decrement. Similarly, logical operations like AND, OR, complement, XOR, these are all several types of operations. So all this data should be handled with the binary form only. So that is why we are solving in elaborate manner. So how to perform simple additions, let us consider in a way. Fine. So in the decimal system, it's very easy to operate the data. But what about in hexadecimal and binary quickly? As fast how you are operating in the decimal, in the same way you should be capable of operating in the hexadecimal and binary also, so that you can save some couple of minutes in solving the question. Right. So let me now emphasize how to solve quickly in the hexadecimal numbers also. To make it clear, let me take some illustration. Say I want you to solve the numbers in the decimal. Anyone can solve very quickly in the decimal system. For example, if I ask you to solve 9 plus 5, your brain can easily calculate that it is 14. If I ask you to solve any other number also, you can do that. Let us say I ask any numbers else also, you are able to do it because there is a fixed path in your brain already linked up with some neurons. It is already habituated. But if I ask the same question in the hexadecimal, let us see how many people can solve this. Say in hexadecimal, I am writing as f plus 5. What is the answer now? I hope you are thinking a bit. So for the first case you didn't think, but second case you are a little bit spending some time. So my intention is to solve this question also in the same way how you have solved for the decimal. How to solve? Here also the answer is same, that is 14H. Clear? Right. So you may be surprised, sir, how could you do this problem? Or some people may know it, no problem. But I am giving a simple tip how to solve the problems in a simpler way. Now, look at this. If you go in a regular method, how much time it will take? Let us consider. For example, I want to solve this question in the regular. 15, F means how much? 15 in decimal. 5 is 5. 15 plus 5, how much it is? 20. So 20 is actually decimal value. How do you write this 20 in hexadecimal? 16 means 10H. So 16 plus 4, it means 14H. So again you have to convert into hexadecimal. So in competitive exam, this process will take lot of time to solve. So to avoid this discrepancy, I am giving you a simple tip how to solve in an easier way. Look at this data. In any kind of number system, for example, if I just go back like to the previous pages, okay, observe here. In any kind of number system, for example, say in decimal system, what is the last quantity? 9. In octal, what's the last quantity? 7. In binary, what's the last quantity? 1. Hexadecimal, it is F. There is a very simple technique which we are going to study now. For example, now observe carefully. In any kind of number system, take 9 is the last quantity in decimal. If you are adding any value to the last quantity in that number system, it means, for example, if you are adding 5 to 9, the answer is whatever added minus 1, 1 carry. That is the answer. Very simple. If you are adding anything to the last quantity in that number system, the answer is whatever added minus 1, 1 carry. That's all. Apply the same concept here also. Apply the same concept in hexadecimal also. Hexadecimal, what is the last quantity? F. If you add anything to this particular F, if you add anything to this particular F, the answer is whatever added minus 1, 1 carry. So this answer is directly present in the hexadecimal. No need to convert back. Is it clear or not? That's a simple logic. So while you are adding anything to last quantity, the answer will be whatever added minus 1, 1 carry. So in competitive exams, if you solve like this, it will take a lot of time. Again, converting from decimal to hexadecimal, you may make some silly mistakes. To avoid that, this is one technique. This is number 1, first one. Second thing, for example, I am taking one more value. Say in decimal quantity, if you observe carefully, 0 to 9, after that the first junction is 10. How many values you can add to this 10? How many single digit data you can add to 10? Very simple, it is 0 to 9. It means this plus 1, you can add 10 plus 1, you got 11, 10 plus 2, you got 12, so on etc. 10 plus 9, you got 19. Then comes the next junction called as 20. It means in the decimal value, 10 can be added with any value called as 0 to 9. Okay, fine. Now observe carefully. I am coming to the same concept with respect to hexadecimal numbers. In hexadecimal, what are the values? 0 to 9, A to F, the first junction is 10H. Now observe carefully, 10H. So how many single digit hexadecimal values can be added to 10H? Obviously it is 0 to F. It means that 10H plus 1 or 10H plus 0, it is 10H. 10h plus 1, it is 11h, 10h plus 2, it is 12h, so on etc. 10h plus f, it is 1f. So what is the next quantity? 20h. Now observe carefully. I am considering these all values, say these all values as some x. I am taking these values as some x. How it happens now, let us see. I am taking this 10h as it is. I am assuming 0 to f as x. I am considering 0 to f as some x. Now obviously what would be the answer? 10h plus x. What's the answer? 1x. Are you able to follow? 10h plus x is 1x, where x is equal to 0 to f. This is number 2. If you have understood these two concepts, the first one, what is the first one? Any value added to f is whatever added minus 1, 1 carry. That is the direct answer in hexadecimal. Second point, 10h in hexadecimal plus x is 1x, where x is anything from 0 to f. So these two things will help you to solve the problems in a very simple way. You need not even spend time to type these letters in the calculator. You can easily become as a calculator. That's what I mean to say. Okay, let us solve the problems very quickly. Just remember these two things. You can solve the problems in simple way. Okay, now understand carefully. For example, I'm coming back to the numbers to be operated in hexadecimal. So I want to perform addition. Okay, addition operation. So how do you perform simple binary addition? Let us say I'm taking the example for binary data. Let the data be anything, whatever it is. Say it is some 0, 1, 0, 1 plus 1, 0, 1, 1. I want to add these two data. Very simple. Remember, it's not decimal, it is binary data, right? 1 plus 1 is 2 anywhere. But how do you write 2 in binary form? 0, 1. 1 plus 1, 2, 0, 1. 1 plus 1, 2, 0, 1. 1 plus 1, 2, 0, 1. That is how we simply perform the binary addition. I am taking two 4-bit data as consideration, but the result is 5 bits. So if it is crossing the size of n whichever taken, this value we simply call it as carry out. The data can be n-bit data. I have taken two 4-bit data. While adding two 4-bit data, the result may cross the 4 bits. The extra bit we call it as carry out. Fine. This can be for 4-bit, 8-bit, 16-bit, whatever it is, based on your choice. Okay. Now I want to perform hexadecimal addition also directly. Now observe carefully. Say FFH plus some 96H. H is indicating these values are hexadecimal numbers. Now tell me, what is the answer? Use the two techniques which were given in the previous page. What are the two techniques? F plus any quantity is whatever added minus 1, 1 carry. 10h plus x is 1x. Now come to the point. Observe, apply those 2 points. F plus 6. What is F plus 6? Don't go for conversion. 15 plus 6, 21. Don't do that. Do it simply. F plus 6. What is F plus 6? Whatever added minus 1, 1 carry. What is 1 plus f? What is 1 plus f? 10h. 10h, right? You know the previous slides. 15 plus 1 is 16. 16 in decimal, but 10h in hexadecimal. 10h plus 9. What's the technique applied? 10h plus 9. 10h plus x. What is the answer? 1x. So here the answer is simply 10h plus 9 is 19. So 195. This is how we can solve the data in a simpler way. Let us solve one more problem. So this is number 1 in hexadecimal. Say number 2. I am taking one more data. Let us see how to solve this other data. Take the other data as say f. Okay, 1 minute. Let me take some different color. Okay, I'm taking other data F, 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 F. I want you to be flexible enough. Tell me, in hexadecimal, how many digits are this? 4 digits. But in binary, how many bits of data is this? 16 bits, because each digit in hexadecimal is 4 bits in the binary. How many nibbles are these? 4 nibbles. 4 nibbles, 4 hexadecimal digits, 16 binary bits. Right. Plus, now tell me the answer. 5, say it is 9, 7, 3. Now, what would be the answer here? What is the answer here? Apply the same concept. You must be quick enough. F plus 3, 12H. F plus 3 means whatever added, minus 1, 1 carry. 1 plus F. What is 1 plus F? 10H. 10H plus 7. 10H plus X, 1X. 10H plus 7, 17H. 7, 1 carry. 1 plus F, 10H plus 9, 1, 9. 1 plus F, 10H plus 5, 1, 5. This is how we can solve in very simple way. So, these are few tips to solve the data in the hexadecimal numbers directly. Fine. Now, you have solved the problem having data as all F's. Now, consider the third case. For example, I give some random data. How to solve now? You please understand. Say the data is something like 7, 5, 9, some E plus 8, 6, 4, 2. I want you to solve this problem. In calculator, it's a matter of 1 second, no problem. But initially, I want all of you to practice in the manual operation so that you will link up a new neuron connections in your brain. That is why scientists say that every day you have to read some book or paper or whatever it is. So there are some lakhs of connections, crores of connections in the brain. When you read a new data, the new neurons will be connected. So your brain will be always active. If you are solving the same regular pattern, then you are not using the effective part of the brain. So now I urge you to solve the problem in the manual method without using the calculator. Tell me what's the answer now? E plus 8. E plus 8. What is E plus 8? E means 14. 14 plus 8, you can solve 22. Instead of that, let me solve like this. E plus 8, I am writing like this. I am giving this data, subtracting 1 from the 8 and giving to E. So this has become how much? F. Okay, it has become F. So E plus 1, I have taken 1 from 8 and given to E. It has become F. What is left here? 7. It means E plus 8 or F plus 7, both are same. Why did I do like this? In order to make the problem easy. So wherever E is present, you can read it as F plus 7. So what is the answer F plus 7? 16H. 16H. So this is 6, 1 carry. Don't apply this concept for all hexadecimal numbers. It is only with respect to E, and other shortcut is with respect to F, not for all. So for remaining data, you solve as per decimal only, but final conversion should be done in the hexadecimal form. Now solve everything as decimal. Tell me 1 plus 9 is 10. 10 plus 6 is 16. 16 is a decimal. How do you write in hexadecimal? 10H. So simply 0, 1. 1 plus 5 is 6. 6 plus 4 is 10. 10 is a decimal value. How do you write in hexadecimal? A. So put it as A. 7 plus 2, 9. This is how we solve the data. E plus 8 is F plus 7, that is 16H. 6, 1. 10 plus 6 is 16. Hexadecimal 10H. 0, 1. 6 plus 4 is 10. 10 is in decimal. We write it as A. And 7 plus 2 is 9. Like this, we can solve the data in a simpler way. So you have to practice further how to solve the problems. I hope you have understood all the 3 examples which we have discussed with respect to hexadecimal numbers. Fine. This is all about the addition, how we perform directly in the hexadecimal numbers. Let us now discuss further how to perform the subtraction. how to perform the subtraction. Before going to the subtraction operation, it is very much important to understand how the values are calculated in the binary with respect to 1's complement and 2's complement. Why is it required? We'll see further in the subtraction operation. Okay. Before going to this subtraction, let us discuss how these binary numbers are actually represented. Binary number representation. Fine. Let us consider an n-bit vector n-bit vector. Say it is some b. B is written as bn minus 1, bn minus 2, so on etc. till b0. b0. So this is b0, b1 and so on etc. Okay, fine. This is how we can represent the binary data. So this data, if you want to represent some integer values like unsigned integer values, there are two types of representing these binary numbers. One is unsigned, other one is signed. So this data can be of two types. One is unsigned and other one is signed. Means whenever there is a requirement of positive and negative number sign of the data, then we go for signed representation. Normally the data can be considered as unsigned. Unless in the question it is mentioned to solve as signed, you don't worry about the sign of the number. You simply solve as unsigned data. So this unsigned data is something like, for example, unsigned, let us take some 8-bit data, 8-bit value. So what is this unsigned? If you take 8-bit data, say here the digits are from D0 to D7. All this data represents magnitude only. There is no question of any sign to be verified. All it is magnitude only. It means if you consider here, say this will represent one integer vector, or this value can be represented as some integer values, as say I want to represent this as integer values, then this will become, so I am calling it as V. So this vector can be written as, so here n is, we can write here, so this b of I am calling this values b of I can be 0 or 1, binary it can be 0 or 1, and similarly I is less than or equal to, I is less than or equal to 0 and less than or equal to n minus 1. So this is the condition. Now observe carefully, this value can be represented as integer value as some v. So we can write this value as v of b is equals to every binary digit should be multiplied with its weight. So I can write it as b of n minus 1 into 2 power n minus 1 plus b of n minus 2 into 2 power n minus 2 plus so on etc. b1 into 2 power 1 and finally b of 0 into 2 power 0. So this will give you some value of this n-bit binary vector. So if you want to consider this as integers like v of b, how to write these values? So tell me, if I take this data as unsigned data, so in unsigned data there is no need to check any magnitude. It means this values can be represented, if it is integer, if it is considered as integer, how many values can be represented? So if you take this as unsigned integers, the range that is possible is simply 0 to 2 power n minus 1. So 0 to 2 power n minus 1. So tell me, what is the value if you take this 8-bit data? So what is the range that can be represented? So 0 to 2 power 8 minus 1. So what is the value? Range is simply 0 to, this is 256 minus 1, 255. 255. So this is how we can write the value 0 to 255. That is unsigned representation of the binary data. Fine. No need to check any sign. You can simply represent the data. Now come to the signed representation. What is the requirement of signed representation of data? Okay, let me just take one simple illustration for it. Say, I am coming to signed representation of binary data. What is signed representation of binary data? Whenever you want to represent the data in the negative form or positive form, you must consider sign of that particular binary data. So if a binary number is some n-bit length, then the last bit, MSB bit, bn minus 1th bit is taken as sign bit. So if I consider, for example, 8-bit data, how do you represent this sign data? It means D7, D6, D5, D4, D3, D2, D1 and 0. So here the last bit, this bit will represent the sign, whereas the remaining bits will represent the magnitude. This is the meaning of sign. So how does it represent? If this bit is 0, then it indicates that this value is a positive value. If the last bit is 1, this indicates this value is a negative value. So this is what we call it as signed representation of data. But the signed representation or representing binary values in positive or negative, there are 3 methods to consider. Okay, how to take the sign to represent the values in positive or negative? There are 3 methods to represent. How to take this consideration? Let us see. So in positive case, all of them are same. So there are 3 methods to represent positive or negative binary value. So what are these 3 methods? Very simple. One is sign and magnitude. Second one is ones complement. Okay. Second one is ones complement. And the third one is two's complement technique. So these are the 3 methods how we can represent the binary data in positive or negative. In all the 3 cases, MSB bit, most significant bit, represents sign. If this bit is 0, it indicates it's a positive value. If this bit is 1, it is indicating negative value. So let us consider by taking an example of 4-bit data. Let us consider with respect to some 4-bit data. How to take with respect to 4-bit data? I am considering now. So here in all the 3 cases, positive value no problem, 0 is positive. Okay, so all the positive values will be starting with 0, but the negative values will take different way let us discuss how it is actually possible. Okay. Let me consider like this. Say it is the first case, this is sine in magnitude, it is 1's complement, and the other one is the 2's complement. Another one is 2's complement. Two's complement. Okay, let me just take into consideration like this. Sorry. Okay, right. Now let us observe carefully. I am taking the binary values like this. The binary bits are B3, B2, B1 and B0. How it is possible? Let us see now. B2, B1 and B0. Okay, B1 and B0, B1 and B0. Okay, let us take one more line here. Okay, fine. So here I am considering with respect to some 4-bit data. How it is obtained? Let us see now. So here I am taking 4-bit data. As see, I am coming with positive, negative. How to solve with both of them? So nothing to worry. You try to understand clearly. So here, say 0, 1, 1, 1. Why am I starting with 7? You'll come to know with respect to representation. Okay. So 0, 1, 1, 1 in sign magnitude. Now tell me, the MSB bit will indicate the positive, sign of the data. So 0 indicates what? Positive. In all the 3 cases, 0, 7 to 0 are same. It means, for example, if I write like this, so this value is in sign magnitude, it is plus 7, in 1's complement also plus 7, in 2's complement also plus 7. In the same way, 0, 1, 1, 0, this is plus 6. So this is 6, this is plus. So 0, 1, 0, 1, 0, this is 5, this is 4, this is 3, this is 2, this is 1 and this is 0. Observe carefully. So in all the 3 cases, these are all same. So this is plus 5, this is plus 4, plus 3, plus 2, plus 1 and plus 0. So this is also same thing, plus 6, so on, etc. This is plus 0. Here also plus 6, so on, etc. This is plus 0. That is fine. So in all the 3 cases, you can observe that the positive values, there is no change. With respect to positive values, there is no change. All are same. But with respect to negative values, the point has to be discussed. Now observe carefully. I am just continuing the same thing so that you can understand easily. So don't forget, this is sign magnitude, this is sign magnitude, this is 1's complement, this one is 2's complement. Right. I'm just extending the line. Okay, fine. So come to the negative values. Observe here, in this case, Say I am taking 1 0 0 0. So this is minus 0, 1 0 0 1. This is minus 1. Sign, it's very easy. Sign numbers. How do you represent sign and magnitude method? Last bit 0, it's a positive value. Same case, if you want negative, write the 3 bits same. Last one should be 1. That is enough. So it is 0 1 0. This is minus 2. 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Let us see what's the meaning. So this is 3, 1 is minus, so minus 3, minus 4, minus 5, minus 6 and minus 7. Minus 6 and minus 7. Okay, right. Very simple. Observe this. You are converting or writing the sign magnitude method as last 0 in all the 3 cases it is positive only. Sign magnitude method MSB 1, it is simply negative. Remaining magnitude remains same, no problem. But come to the next case, observe from here. In 1's complement, this one is 1's complement. What is 1's complement? 1's complement is just complementing every bit from either 1 to 0 or 0 to 1. So, observe carefully. Here, 1's complement of 1, let me tell you like this. Take the example here. I am just writing as a rough here so that you can follow easily. Right. So, if you observe carefully, 0 0 0 1 is the data. So, it is positive, this value is 0, so indicates positive. What is this quantity? 1. So, it is plus 1. I want to find out minus 1. How to find out minus 1? Just find the 1's complement. What is 1's complement? 1's complement is obtained by complementing every bit from either to 0 1, 0 to 1 or 1 to 0. So, how we got this? Complement all the bits 1 1 1 0. So, this is the meaning of minus 1 in 1's complement technique. The same thing can also be obtained by subtracting the data. 0 0 0 1 was plus 1. I want to find out minus 1. So, to obtain minus 1, what to do? Just complement each bit. Complement each bit. So, you got as 1 1 1 0. So, this is equivalent to minus 1 in 1's complement technique. Are you able to follow? Right. So, this value can be obtained by in other type, like this is first case. In the second one, this can be obtained by subtracting. So, what can be obtained? 1's complement. 1's complement can be obtained by subtracting every bit from 1. So, if we subtract every bit from 1, what is the value we got? Very simple, 0 0 0 1 is the case. I want to find out 1's complement, subtract every bit from 1. So, what is the value obtained? If you subtract every bit from 1, 1 minus 1, 0 1 1 1. So, this is the same value which was obtained here. Now, tell me, how many bit data is this? 4-bit data. If it is 4-bit data, what is the range that can be represented? For 4-bit data, the range for unsigned is simply 0 to 15. 0 to 15 if it is unsigned. So, tell me, what is the equivalent value of this 111? 15. It means 1's complement of a 4-bit data can be obtained by subtracting the data from 15. Let me analyze this thing. Very easy. So, for 4-bit data, the range of values are 0 to 2 power 4 minus 1. Okay, that is 0 to 15. It means to get the negative value in the 1's complement technique, it is very easy to subtract the corresponding number from the 2 power n minus 1. It means here it is 0 to 2 power n minus 1. So to get the ones complement, you subtract the data from 2 power n minus 1. So to get minus value, it is enough to subtract from 15. So I want to have minus 1. So subtract 15 minus 1. What's the value? 14. 14 is 1110. That is how we can get the ones complement technique. Right. It means the conclusion here is, what is the conclusion here? The conclusion here is subtract the number from 2 power n minus 1, where n is n bit, to obtain negative value of the number, negative value of corresponding number. So whichever the number you want to find out the negative value, you just subtract the number from 15 if it is 4-bit data. Right. That is about ones complement. Come back to the previous page. Okay. Now you tell me, from this discussion, what is minus 1 value? That is 1110. So here, if you observe carefully, this 110 is actually minus 1 value. Fine. So 111 should be what? Minus 0. Okay. Right. Now tell me, the next value should be how much? 15 minus 5. So you subtract this value. This is actually minus 2. This is minus 3. This is minus 4. Minus 5. Minus 6. This is minus 7. It means in ones complement technique, minus 7 is given as 1000. And this is actually minus 0 quantity. That is the difference here. Because ones complement of all zeros is all ones. That is minus 0. That's about the ones complement and sign magnitude technique. It means, what did you understand from this? Here, in both sign magnitude and ones complement method, the range can be from minus 7 to plus 7. Okay. So in both the cases, you got plus and zeros. So you got plus 0 and also minus 0 in both the cases. But come to the third case. What is 2's complement method? 2's complement method. In case of 2's complement is obtained by 1's complement plus 1. 1's complement plus 1. There is some generalized equation, very simple. R's complement is given as R minus 1's complement plus 1. So very simple. If I want to find 2's complement, negative values in the 2's complement, what is the technique now? So very simple. Let me take now example 0, 0, 0, 1. 0, 0, 0, 1. Tell me, is it a positive value or negative value? 0 indicates what? Positive. And this is the data. This is the data. Accepted? Right. Now observe carefully. How much you got this? So this is 1, positive 1. This is plus 1 with respect to 2's complement. Now, I want to find out what is minus 1. So, in 2's complement method, to find out minus 1, what's the technique? You have to find out r minus 1's complement plus 1. So, what is the 1's complement of this? The 1's complement is simply 1, 1, 1, 0. This is 1's complement plus 1. It is 1, 1, 1, 1. So, this is the 2's complement of the value. 2's complement of this data. It means minus 1 is equivalent to 1, 1, 1, 1 in the 2's complement method. Come back to the previous slide. Observe carefully. Here 1, 1, 1 was actually 1, 1, 1, all the 4 ones was actually minus 1 value. I want you to think a little bit. Okay. So, minus 1 is 1, 1, 1. Observe carefully. In both these two methods, you are having plus 0 and also minus 0. Plus 0 and also minus 0. Plus 0 and also minus 0. But observe in 2's complement, you are not getting minus 0 value. Okay. Why? If you take 0's complement, if I take 0's complement in 2's complement, 0, 0, 0, take 2's complement of this value. First find out 1's complement. What is 1's complement from this? 1, 1, 1, 1 plus 1. What do you obtain? 0, 0, 0, 0, 1. So, it is crossing the bit length. So, the 2's complement of 0 is 0 only. Okay. So, we do not take into consideration. Now, observe carefully. Here, this value is minus 1. Now, tell me what should be this value? If you have understood till now, this should be minus 2. It is minus 3, minus 4, minus 5, minus 6, minus 7. Now, I want you to think little bit for this. Okay, if you are not able to match, 1 minute. Let me just write like this. If you take from the beginning, okay. Now, consider from this. So, here this is actually equivalent to minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1. It means that in the 2's complement representation, you didn't get the range of plus 1, plus 0, plus minus 0 or minus 7 to plus 7. You got a range of minus 8 to plus 7. It means there is one important conclusion out of this. So, observe carefully. In the 2's complement method, here I am taking the 2's complement method. 2's complement method for 4-bit data. For 4-bit data, the range possible range is minus 8 to plus 7. If I write the generalized form of this, for signed representation of data, if I write the generalized form, I can say that we can represent 2 power n minus 1 to plus 2 power n minus 1 minus 1. If I take n as 4, example n is 4, it can be minus 2 power 4 minus 1 to plus 2 power 4 minus 1 minus 1. That gives rise to minus 8 to, what is this value? 7 plus 7. It means you got the range of values as minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0 to 7. So these all are 8 positive values. Now observe carefully. There is no minus 0 and hence there must be 8 negative values also. 8 negative values. So observe carefully. If I take a 4-bit data, the last bit B3, B2, B1, B0. This is for sign. So if it is 0, what is this range? 2 cube. So 0, 2 cube means 2 cube, 8 positive values and 1 is negative. So 2 cube is there, 8 negative values can be represented. So that is why it has started from minus 8 to minus 1, 0 to 7. So that is the difference between the sign and magnitude representation, 1's complement representation and 2's complement representation. So dear friends, I hope you have understood clearly how the representation differs with respect to all three. But in most of the cases in modern computers, the data is represented in the 2's complement method only because of the advantages it has got. Sometimes the problem goes wrong if you consider the 1's complement method or the wrong method of applying subtraction by using sign and magnitude method. So that is why in modern computers they go for 2's complement representation. So let us take the subtraction operation now and see what is the difference. So you should understand that in modern computers all the data inside it is represented in the 2's complement representation only, because 2's complement representation doesn't give the erroneous results. So subtraction using 1's complement method or sometimes addition also will give you error in 1's complement, but 2's complement it is not possible or not produced. You can take some examples and check it further. Okay, so let us now discuss the subtraction operation. Fine. So I am taking 8-bit data now. Till now we have solved the 4-bit data. So tell me in 8-bit data, how do you write this subtraction? Let us see now. So observe carefully. So subtraction, let us say I want to subtract 97H minus 73H. So what is the answer now? Directly I can tell in hexadecimal. 7 minus 3 is 4, 9 minus 7 is 2, 4H. But how is the subtraction done in the computer? I am taking two variables A and B. Okay. So subtraction can be done in two ways. Let me write like this so that you can understand easily. So subtraction is done in the computer in different way. I am taking A and B. A minus B is written as A plus of minus B. A plus of minus B. Okay. So you observe that how to do this. A plus of minus B. Clear? So to find the negative value, you may take 1's complement or 2's complement. But 1's complement will give you erroneous result sometimes, which is not provided or produced with respect to 2's complement. That is why we go with the 2's complement method of operation. So observe here. Here no problem. 97 is as it is, A is A, 97 remains unchanged. But what to do now? I want to find out minus B. I have to find out what is the value of this. Now tell me how to find out negative of this data. So simple logic is, now tell me how did you find 1's complement? Subtracting the number from 2 power n minus 1, okay, 2 power n minus 1. So the shortcut is in 2's complement, the shortcut is you subtract this data, you find out the 2's complement. How do you find 2's complement of this? Tell me. 0, 1, 1, 1, 0, 0, 1, 1. This is 3, 7, 3, 7. So how do you solve this? Minus value, take the 2's complement. So 2's complement, first 1's complement is 1, 0, 0, 0, 1, 1, 0, 0 plus 1. How much you get? 1, 0, 1, 1, 0, 0, 0, 1. So this quantity, what is this quantity here? How much you got? 8D. This is 8DH. Okay, fine. What's answer now? You're adding negative value of 73. Okay, so tell me what's answer? 7 plus D. D means 13 plus 7, 20. 20 is a decimal. How do you convert in hexadecimal? 14H. So 4, 1 carry. 10 plus 8, 18. 18 is a decimal value. You write as 12H in the hexadecimal quantity. So this is 2 and this is 1. This 1 is carry. Now tell me, can the result contradict when you solved in the manual method? How we perform this manual method, and this one is processor method. Okay, so can the result contradict to each other? No. That is why you discard this particular carry. Discard the particular carry. So what to do with this carry we'll see later on. Okay, so discard this particular carry. So this carry is internally complemented to make the result to be equivalent when operating with the signed data, unsigned data. That is why we don't worry about this, we simply discard. Okay, so the answer is same. Are you able to follow? It means you can solve in either ways, whichever is easy, it's better to solve like this. Now, for finding the 2's complement, how did you solve? You have taken 1's complement first, then you have added 1 to it, then you got the corresponding 2's complement. Okay, but the 2's complement of data can be directly obtained by subtracting a particular digit, whichever you want 2's complement, from 2 power n directly. It means 2's complement of 4-bit data is 2 power 4 minus number. So this number is 4-bit data. Okay, right. So for example, I want to have say minus 7, 0, 1, 1, 1 is plus 7. If I want to have minus 7, just subtract this data by from 2 power 4. What is 2 power 4? 16. So this is simply equivalent to 16 minus 7, 9. 16 minus 7 is equals to 9. So minus 7 is equivalent to 1001. That is the meaning. I hope you have understood clearly. That is how you have to perform the data. Is it clear? This is how we have to perform the 2's complement technique. Is it clear? So you can easily solve the resultant value. 8D can be obtained like this. So minus 73, one simple shortcut to find out negative of the value. Subtract the first digit from 16, second digit from 15. You will get 16 minus 3, 13, 15 minus 7, that is 8. So minus 73 is equal to 8D. So that is how we can solve the subtraction. So you can practice some questions, like you solve some questions like 84 minus some 16. How to solve? Second problem, you solve some question like E3 minus 7B. You solve some questions like this. It will be easy. So let us continue this topic. We try to solve these questions. Let us continue the problems which we were discussing in the previous topic. Say I want to subtract 1684H minus 16H. It's very simple. Let us solve in both the methods, like manual method and the processor method also. Okay, so let us first solve in the manual method. Don't forget that you are working with the hexadecimal numbers. It is not decimal numbers. So tell me, what is the base in the hexadecimal numbers? If you can recollect, it is 16. You must get habituated to that. So here this is not 10, it is not a decimal number. For example, say if you solve in the decimal number 84 minus 16, anyone can solve. From childhood we are habituated. So you cannot subtract 6 from 4, we take a bar of 10, 7 is left here, 14 minus 6 is 8, 7 minus 1 is 6, 68 is in the decimal number system. So in this decimal number system, the place values are 10 power 0. For example, say in the decimal system, one minute, it is just in the decimal system, if you consider here, this is 10 power 0, okay, and this is ones place, this is tens place, ones place and tens place. But which number system is this? Hexadecimal number system. So what is the place value here? It is 16. So it is 16 power 0, 16 power 1. Okay. Now, if you do in a shortcut way, very simple, what's the answer here? You cannot subtract 6 from 4. So take a borrow. How much borrow you are taking? 16. This 16 we are writing in the hexadecimal form as 10H. Both are same. So 16 plus 4, 20 minus 6. What is 20 minus 6? 14. What is 14? E. Solve everything in the decimal method. Just presentation of data should be done in hexadecimal number. That's it. So I am just making you to understand how fast we can do in manual calculation also instead of using a calculator. Right. So what is left here? 7. 7 minus 1 is, by the way, it is 6e. So in decimal system we solve like this, assuming the base as 10 or considering base as 10, but this is not 10, this is 10H, 16, base 16. That is how you solve. And this is the method involved with the manual operation. Now, for example, the same problem can be done in the processor method. How is the processor doing? Processor will perform as like a minus b is equals to a plus of minus b, a plus of minus b. So, to find out this value, 84 remains as it is, plus you must find out minus 16 value. So, very simple. How do you find out minus 16 value? You must take the 2's complement if it is in binary. Shortcut, I told you that to find out the negative value of a hexadecimal data, you have to find out the 16's complement. Why? In binary, base is 2, so we find 2's complement to get the negative value. In hexadecimal, what is the base? 16. So, to find out negative value of a hexadecimal data directly, you have to find out the 16's complement. How? Very simple. I am giving you simple shortcut. So, how to find minus 16? Let us say this is the data. I want to find minus 16. The first nibble, subtract from 16. Whatever the next values are there, let the length be anything, whatever it is. You just subtract from 15. Why? In finding 2's complement, you are adding 1 only to the LSB. 1's complement plus 1. So, that is why only the first nibble should be subtracted from 16. Remaining all are 15. That's it. So, this is a shortcut. So, how do you solve this? So, if you solve this data, what is the answer now? 16 minus 6, 10. 10 means A. 15 minus 1 is 14. That is E. It means that minus 16H is equivalent to EAH. That's the meaning. So, now I have to add minus 16 value to this. So, EA, you need to add it. So, how much value you get? It is same. A means 10 plus 4, that is 14. 10 plus 4 is 14. 14 is E and 14 plus 8 is 22. Or shortcut what I have already discussed is E plus 8 can be written as F plus 7. Both are same, so that you can solve easily. E plus 8 or F plus 7 both are same. F plus 7 is how much? 16H. So, therefore, 6 and 1 is carry. So, you try to discard it because this was obtained because of addition, internal addition. Therefore, so that don't worry about this carry. So, you have to discard carry in the subtraction operation. What to do with the carry we shall discuss later on in the subtraction instructions. So, this carry is internally complemented so that the result will not contradict. Okay. So, while we consider about the borrow, we will come to know this point. So, this is how we have to perform the subtraction operation. So, the simple thing you have to understand is that finding 2's complement of a binary value is as if calculating its negative quantity. Similarly, Finding the 16th complement of a hexadecimal value is same as finding its negative quantity. So these 2 points would definitely help you in finding the arithmetic and logical operations. So you must be more flexible to write the data in binary, hexadecimal, so on, etc. So these are very important to solve the problems. So from the beginning till last, whatever you solve, every data will be in the binary form only. Inside the microprocessor, the data is in binary only, but we cannot write the lengthy binary data ones and zeros. To make it in a simpler way, we denote in the hexadecimal representation. So inside the processor, everything will be binary only. For avoiding the waste of time, we solve in the hexadecimal representation. So these 2 points you must consider, right? Okay. Now let's go for the other notation of sign data. So by now, I hope that you have understood very clearly what is the meaning of signed and unsigned data. So unsigned data, no need to check about the sign of the number. All the bits will be considered as magnitude. And in signed representation, you can have a sign and magnitude method or 1's complement method or 2's complement method. But in solving the problems, 2's complement method is considered in the most modern computers, as the result is not going with the erroneous value. Because if we go for 1's complement, there are some cases where the data may be error. So that is why in all the modern computers which are present nowadays, will follow the 2's complement representation of the binary data with respect to negative quantities. Fine, right. Now let us consider the other data. Say that I am considering some 8-bit binary value, or I say 8-bit signed data. Let us consider like this: 8-bit signed data. 8-bit signed data. Tell me, for n-bit signed data, what is the range that can be represented? What is the range that can be represented for n-bit data? So the range possible is, what's the range possible? This is minus 2 power n minus 1 or minus 2 power n minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. So if I consider 8-bit signed data, so n is 8, 2 power 8 minus 1, this value is simply minus 2 power 7 to plus 2 power 7 minus 1. This will give you minus 128 to plus 127. So don't forget, in 2's complement representation, you won't get minus 0 and plus 0. Instead of that, the number range will be started from minus 1 to minus 128. Very simple. How it is, let me just elaborate so that you can understand the problems in a very simple way. So I emphasize you people to understand the concept, basic concept very clearly, so that you will not find trouble in solving the problems. So let us consider this 8-bit signed data. How to solve this? Let us consider. So these are very important in GATE question. This data is looking very simple, but we shall solve some questions where you completely depend on this basic data. It looks very simple, but very important in solving the data. Fine. Sometimes, what is the meaning of this signed data for 8-bit notation? I am showing clearly. What is the range? How you get this? Let us see. Fine. How to understand this data? Okay. Fine. So let me take this 8-bit signed data. So here I am considering the data something like this. Fine. So in 8-bit signed data, the D7 bit is considered to be MSB, that is a sign bit. sorry. So D7 bit is sign bit and D6 to D0 will be magnitude. Okay, this is sign bit. Let us see what happens here. Fine. So you observe carefully. There are a few important things to be noted down here. How to interpret this data? Okay, this is 8-bit signed data. 8-bit signed data. Okay, if this bit is sign bit, I am taking this bit as sign bit. For sign bit, okay. If this bit is 0, it indicates positive value. If this bit is 1, this indicates the negative value. So how to solve this problem? Let us consider. So magnitude will be for only 7 bits. So 2 power 7, what is the value? 128. It means that it is possible to represent 128 positive values and also 128 negative values. Fine. So take from 0. How many bits are this? 7 bits. 1, 2, 3, 4, 5, 6, 7. So I am just writing the value in the hexadecimal and also decimal. There are some important conclusions to understand from this. So tell me, what is the equivalent hexadecimal value of this? 0, 0. In decimal, this is simply 0. Right. Come to the next one. So on, etc. How many values can be done? 0 is a positive value sign and 1, 1, 1, 1, 1, 1, 1. This is the maximum value, means 128 combinations. So this value will be 0. This value will be 0. Sorry, 7F, not 0. It is 7F. It is 7FH. Okay, tell me, what will be the decimal equivalent of this? Think logically. These are 128 positive values. Means if this value is 0, this value should represent how much? 127. It is just logical thinking, nothing else, nothing to worry about it. So it is just logical thinking. Okay, how to follow this? Let us see. Right. So this is simply 127. Right. Now come to the next one. I am just placing one line here so that you can understand easily. Right. Now come to the point. Say I have taken 1 0 0 0 0 0 0 0. Tell me, what is the equivalent hexadecimal value? 80H. 80H. So on, etc. If you go, these all should be 128 negative values as per sign representation. So the maximum value in this 111, 1111. So this value in hexadecimal should be FFH. FFH. Now observe carefully. It is FFH. FFH. Right. Now look at this. This is 2's complement method representation. Tell me, these all values are negative values of some x positive value. It means that, for example, take a value -1. Let me consider like this. Say, take a value 0, 1H. What is the meaning of 0, 1H? 0, 0, 0, 0, 0, 0, 0, 1 in binary form. Okay. So this is 0, 1H. Tell me, is it positive value or negative value? This is 0. So this is definitely positive value. Now if I want to find out -1H, either you take directly 16's complement of this, or you can take the 2's complement after converting into binary form. I am directly writing as 16's complement. So tell me, how do you solve this? What is the negative value of this one? How much it is? This is 10H. It is F. You subtract 16 minus 1 is F. This is F. it means that the conclusion is minus 1 is actually FFH. Now think properly. FF is the negative value of 1, not minus 1. Be careful. FF is not negative value of minus 1. FF is a negative value of 1. Come to the point. FF is equivalent to minus 1. Now tell me, how many negative values are possible? 128. It means if you go on writing, the other value will be minus 2, so on, etc. This value should be minus 128. It is a bit confusing. Sir, you may raise a doubt. Sir, 80H means it is 1000. If I take the 2's complement, the same value is obtained? True, fine. But in 2's complement representation, we don't have negative 0 because the range is 0 has already gone to the positive range. So therefore, the negative range FF is indicating minus 1. So definitely this 80H should be taken as minus 128. That is how the range has become minus 128 to plus 127. So this conclusion is very important. You'll get in several type of questions. Okay. So that is about the 8-bit sign data. So in the problems, you must consider like this. Let the data be any n bit. In signed representation, the MSB is taken as sign. So 0 is positive, 1 is negative. So that's about the signed representation of data. Sometimes what happens is, they may give you some problem asking you to find out sign extension. Okay. What is the meaning of sign extension? So what is sign extension? To represent a number in 2's complement form using a larger number of bits as per the size of the data, then you repeat the sign bit on the left side. Okay, as many bits you want, you just go on repeating it. What's the rule? In order to represent a number in 2's complement form using a larger number of bits as compared to its given size, then repeat the sign of the bit on the left side, left part of the digits or bits. Let us consider what is the meaning of this. For example, consider there is a problem. Let me take one simple problem so that you can understand easily. So, take a simple problem. Represent a 4-bit data plus 7 in 8-bit form using sign extension. So how do you do this? Very simple. First you understand carefully, 4-bit data, you write plus 7. So whenever plus is given, you must understand it is not unsigned data, it is signed data. When the sign is represented plus or minus, you should know that it is a signed data, not unsigned data. In unsigned, don't bother about the sign, only magnitude. So plus 7, how many bit data it is? 4-bit. How to write plus 7 in 4-bit? Plus 7 is given as, 7 means we know 7, 0, 1, 1, 1. So these 3 bits are for magnitude, this is for 0. 0 means positive value. So that is plus 7. Accepted? Right. Now I want to write this data in the 8-bit form. What is 8-bit form? So this is the value, but I want to represent in the larger number of bits. How to write? Very simple. What is the sign bit? 0, positive. So in the sign extension form, we just write the number 0, 1, 1, 1. Whatever is the sign bit, just go on repeating to the length whichever is mentioned in the question. That's all. That is one example. For example, I ask the same thing to be done for minus 7. Same thing should be done for minus 7. So how do you solve for it? Very easy. So if you want to write for minus 7, how it is possible? Let us see now. Very simple. First you write what is minus 7. What is minus 7 in 4-bit representation? Okay, minus 7. How do you write 2's? I am asking about 2's complement representation. Okay, right. So, how do you write this? Very simple. First you write 7. 0, 1, 1, 1. This is 7, right? 0, 1, 1, 1 is 7. I want to find minus of it. Accepted? Minus of it. First you do that. This one is positive, no need of any 1's complement, 2's complement. It is negative. To represent negative values only we go for 1's complement or 2's complement method. Right. So, it is 7. I have to find out minus value. So, in 2's complement method, how do you solve? To find the negative value, just subtract from 16, directly you will get it, or 1's complement plus 1. So, what is the 1's complement of this one? So, shortcut. What is shortcut? Simply write like this. Whatever the data you want, minus 7 you want, just subtract directly from 16. How much you get? 16 minus 7, 9. What is the binary pattern of 9? What is binary pattern? 1, 0, 0, 1. Understood? So, this is minus 7. Therefore, minus 7 is equals to 1, 0, 0, 1. Now, this data I have to represent in the which one? 8-bit form. Take the sign bit. This one is negative, right? Negative value. So, take the sign bit, go on repeating. What is the value now? Repeat this value. So, 1, 0, 0, 1 was the value. Repeat the sign bit for remaining number of bits. I want in the 8-bit. So, you just write. That is how you get. If you want still in shortcut, we can do in this way also. I want minus 7, right? Which bit form? 8-bit form. I will write like this. I can write this minus 7 as minus 0, 7. Now, directly find out the 16's complement, you will get the same answer. So, directly find out the 16's complement. So, what is the value you get now? Okay, how do you solve? What is the value? 16 minus 7, 9, 15 minus 0, 15, F9. This is same as F9. That is the advantage of finding the problem in 16's complement method to find out actually 2's complement. So, in 2's complement you have to convert into binary, again find the 1's complement plus 1. Instead of doing that, directly you can solve in the 16's complement. Right. That is about the problems which are present in the conversions and sign bit. Remaining problems like other fractional part in binary number system, these all would, will be discussed or would have been discussed in the digital electronics part. So, nothing to worry about it. I am concentrating whichever is required for the computer organization subject. Fine. Till now, we have discussed few topics or few points about the number systems, which is one of the important tool for understanding the subject. You are all engineers, you know very well how tools help us to do the job. I may be one good healthy person or a very strong person. Okay, in my personality it don't look like, don't worry about it. So, let us say you are a good bodybuilder, fine. So, you have got lot of strength. You want to remove a small screw from any device. Even though you have got lot of strength, the small screw cannot be removed by your strength. You need to have a tool called a screwdriver. So, here your strength doesn't matter, tool is important. The same way, to understand this subject, number systems is one of the important tool for representing the data. Unless you know the concept of numbers or representation of this binary data, you cannot follow the other part of the syllabus. So, that is why I have enhanced a lot of time on representing this number systems and how to solve this data. Fine. Now, that is one tool. The second tool to understand the subject is memory concept. So, what is memory, how the data is stored in the memory, how do you address, how the microprocessor addresses, so on, etc. To understand that, let us see one of the important medium of communication for the data between the three blocks called as processor, memory and input-output devices. These are the basic functional units of a computer. So, one is I/O device, other one is I/O means input-output device, CPU, processor, other one is memory. So, let us discuss how these three communicate among themselves. I'm calling it as system bus. So, if you consider this path, how it is possible, let us see. Okay, I'm again coming back to the same block diagram. So, here we observe this is the fine. Okay. So, this is the IO block, this is the microprocessor or CPU, and this one is the memory. They are connected between them through some path. So, this path we are calling it as bus. This path I am calling it as bus. This is what we call generally as bus. So, bus is simply a group of wires or conductors used for communication between processor, memory and the input-output devices. So, if it is not visible, let me just remove this one. Okay, right. So, this is what we are calling it as bus. Okay, so this part is bus. So, what is this bus? Bus is simply a group of conductors or wires used for communication between processor, memory and the input-output device. That is what we call it as bus. So, don't forget that microprocessor is one IC. There are different types of microprocessors in the market, but in initial years, one successful microprocessor which was in the market was 8085. So, 8085 is an 8-bit microprocessor. So, what is the meaning of 8-bit microprocessor? It can operate on 8-bit data in the arithmetic and logic unit. That's what we call it as 8-bit microprocessor. In other words, it can take 8 bits of data at a time from the memory. It cannot take more than that. That's what we call it as word length of a particular microprocessor. How many bits can be parallelly accessed from the memory or processed in the arithmetic and logic unit of a microprocessor is called as word length of that particular processor or a computer. Right. So, I'll be discussing this basic concept with respect to this processor so that you can understand the rest of the game very easily. Very easy. For example, say you know how to ride one bike, any company. If you know how to ride a bike, it is not a difficult task to ride some Bullet or Enfield, whatever it is. It means only little bit of change in the gears or the type of braking, starting, kickstart, whatever it is will be different. It means that there are hundreds of types of microprocessors in the market. But if you understand one microprocessor thoroughly, rest of the game goes very smoothly. So, as it is one of the basic type of microprocessor, I would like to discuss the remaining topic with respect to some 8085 up to some extent. Later, I will be generalizing the design of the computer, like computer organization. So, you should know organization means implementation of the design. So, in that orientation, I will be just taking the reference of 8085. Later on, we will be discussing the generalized concept. Okay, fine. So, what is the meaning of bus? Bus is a group of wires or conductors. For example, आपने देखा होगा एक कंप्यूटर में एक स्ट्रिप, प्लास्टिक स्ट्रिप की तरह चलते रहेगा. That group of wires is called as bus. Bus is simply some group of such wires. That is what we call it as bus. So, the processor communicates with the memory and the IO device by using 3 different types of buses. One is called as address bus, other one is called as data bus, and third one is called as control bus. Bus is something like a road. For example, you are traveling in a road. What are the different parameters you can think about? Is a road one way or two-way direction? What is the purpose of the road? Like, is it a normal street or a town road or a national highway, so on, etc. Highway would be some 6 lane, 4 lane, 2 lane, different sizes. Fine. So you should know, in the same as you are comparing a road with respect to buses. So let us consider bus as a road. You should know what is the purpose of this bus and what is the length of the bus. Length means not the wire length, how many wires it is. So 6 lane or 4 lane or 2 lane, that is called length of the bus. Third one is what is the direction of the bus. So these are the three important parameters you should understand about the bus. So system bus is actually physically visible to the designer of a computer. We can see a bus if you open the cabinet of a computer. You can easily observe this. Sometimes these lines are printed on a plastic surface. We call it as printed circuit board. When the number of wires are more, you cannot connect all the wires. It becomes clumsy, complicated. To make it simple, the circuitry is printed on a board. That is what we call it as printed circuit board. And hence, we can now see what are the purposes of these three buses. Come to the first one, address bus. I told you three parameters, purpose, length and direction. First parameter, purpose. What is the purpose of address bus? Address bus has got two purposes. Let me tell you what is the purpose of this. Address bus has got two purposes. Number one, the purpose of address bus is to transmit or transfer address of memory. I am denoting memory as M/M or IO from microprocessor. That is what first purpose of address bus is. Second purpose is to decide how much memory can be connected to the processor. So address bus defines the maximum memory, or instead of saying how much memory, I can also say maximum memory that can be connected to the microprocessor. So that is given by the address bus. So this relation of address bus is given as 2 power n is equal to n. This is the very basic formula which is very, very important in all the rest of the problems. Whether it is instruction or memory, whatever it is, without this notation, you cannot go further. So address bus decides or defines maximum memory that can be connected to the microprocessor, given by the relation 2 power n is equal to n, where the value of small n is indicating number of address lines. Similarly, capital N indicates number of address or memory locations. Number of address or memory locations. What does it mean? We shall discuss in the problems. So this is one important thing. So this is the first parameter, purpose of the address bus. That's the purpose, right? Now the next one is length. Before going to the length, we shall see what is the meaning of this notation. Okay, so here number of address lines means number of wires a particular processor has got. Observe carefully. A processor is one IC, okay. Say it is 8085 microprocessor. Every processor will have some pins to be connected to the devices or memory, whatever it is. So 8085 is a 40 pin IC. Generally, it's called as notch. This is called as notch. On the left side, you'll find a small dot. This indicates that pin number 1 starts here, pin number 20, pin number 21 and pin number 40. Every pin has got certain purpose. So every pin is called to be a signal. We are just going to study what are the different pins that are possible for a processor and how it must be connected to the devices, right? So here number of address lines means this number of address pins, that is n. So processor has number of pins and these lines or pins are connected to the memory. Memory is also some IC like RAM, ROM. So this value is called to be n. So how to understand? Let us see based on this notation. Fine. So as I told you, we shall discuss the topic with respect to 8085 so that you can understand easily. So 8085 is 8-bit processor and the second parameter is length of the address bus. So come to the previous slide. I told you first one is address bus. There are three parameters: purpose, length and direction. So this number of address lines in case of 8085 is 16. So what is length? Number of wires it has got. So the second parameter with respect to 8085 is 16. It means a 16 bits in length. The length of address bus in 8085 is 16 bits in length. Why are we calling 16 bits in length? What is the meaning of 16 bits in length? Observe carefully. Here, for example, if there are two address lines, 1 and 2, already you know what's the meaning of bit. What is bit? Bit stands for 0 or 1. Are these numbers going on the wires? No, these are electrical signals. Therefore, these are voltage levels on the lines. So, as per the TTL notation, what is the meaning of 1 and 0? So, 1 means any voltage level on the wire from 0 to 0.8 volts, that is representing 0. Okay, logic 1 means any value from +2 to +5. So, this represents logic 1. So, these levels between this 2 and 0.8, these levels are called to be invalid, means they are not valid. So, the processor cannot understand this value, insignificant or indefinite. Okay, how to avoid that we shall see later. So, 1 means any voltage level on the wire from 2 to 5, 0 means anything from 0 to 0.8. Don't get confused with the 0 volts and logic 0 data. That is why we call it as logic 0, not simply 0, because 0 means anything from 0 to 0.8. 1 means 2 to 5. So, now observe carefully. That is about the TTL representation. Now, if you have got, let us say, 2 wires. Each wire can support only 1 bit, either 0 or 1. Now, if there are 2 wires, how many combinations are possible? 0, 0, 0, 1, 1, 0, 1, 1. It means one wire can support only 1 bit of value, 1 bit of information at any given instant of time. It means as many number of lines are there, wires are there, so many bits are possible. It means this is 2-bit length. Now tell me, the number of address lines in 8085 is 16, means A0 to A15. How many wires are there? 16 wires. It means how many bits parallelly can be transferred at a time? 16 bits. That is why we call it as 16-bit in length. The length of address bus in 8085 is 16-bit length. Who decides this? Manufacturer. Who decides? Manufacturer. It is not in our hands. Simple example. You have got a mobile. Will you decide your memory in the mobile? No. The manufacturer will say this mobile is having 64 GB of data memory. So, this is the price of the mobile. Other mobile can hold only 32 GB of memory capacity. So, this is the price. Based on your budget, you will buy the mobile. So, manufacturer will decide how much memory should be possible for the processor which is inside the mobile. Designer will decide. So, address lines are not in the hands of the user or programmer. They are based on the designer, manufacturer. Fine. So, 16-bit length is the address bus for the 8085 processor. The third parameter is direction. Now, tell me, what is the purpose of this address bus? Address bus is used to send the address of memory or IO device from the microprocessor. If you observe carefully, here to make it simple, I have drawn the diagram in other way. But always understand that microprocessor only will send the address to memory or address to the IO device. So, this will send these are all different address lines, okay. So, that is the meaning. So this will send the address to either memory or either to IO device. Memory will not send address to processor, or IO will not send to that address to microprocessor. So the direction of address bus is what? Unidirectional. That's the meaning. So direction of address bus is unidirectional. Okay, that is how we can understand the direction of address bus. So I told you three parameters. One is purpose, length, and the third point is direction. Okay, now let us consider some concept of memory now. Before going to the data bus, let us see how actually we should understand how much memory can be connected. The second point what we have discussed is how much memory can be connected to the particular microprocessor. Okay, we shall see what kind of memory is that. Now I am discussing concept of memory. What do you understand by memory? See, there are two types of memories. Already I have given you some basic thing. One is primary, other one is secondary. Okay, other one is secondary. Primary again has got two parts, that is RAM and ROM. RAM stands for random access memory. This stands for read-only memory. Again here you have got static RAM, which depends on voltage for storing the data. This depends on dynamic RAM, depends on charge. The data is stored in the form of charge. It is stored as voltage. Bit is stored as voltage. ROM, again there are several types: masked ROM, programmable ROM, EEPROM, so on, etc. We shall see later. Once you understand this one, remaining is very easy to follow. In secondary memory also we have got different types like CD, okay, DVD, Blu-ray disc, magnetic tape. Similarly, you have got hard disk, okay, hard disk. These are all different types of secondary memories. You've got hard disk, okay. Fine. These all are outdated almost, but nowadays we have gone with flash memories, very fast memories. So try to understand clearly that the primary memories are very fast memories as compared to secondary memories, which are slow and large capacities. So primary memories are fast and less capacity as compared to the secondary memories. So primary memories are less capacity but fast. These are more capacity but slow. Fine. But later on in the latest computer era, we have gone for very high capacity for solid state memories also, solid state devices. So hard disks are nowadays made up of solid state devices, very small compact size, even 1 TB, 2 TB are also available, terabytes are also available. So now we are going to discuss memory which is in terms of primary, like primary memory. Observe here, random access memory, read-only memory. Okay. What is the meaning of random access memory? The name itself indicates like you can access any memory location randomly with the same time. Means to take the data out of the memory location is same either for the first location or the last location. That is called as random access memory. Fine. Now in that scenario, whether it is RAM or ROM, both are random in nature. Let us say this is some memory having some memory locations with some data. The time taken to access the first location or the time taken to access the last location is same. That is the actual meaning of random access memory. It means that whether it is RAM or ROM, both are random in accessing. Means to take the data, let us say this is the data. To read the data from this location, say I require 10 nanoseconds. To read the data from the last location also, it requires 10 nanoseconds. That is the meaning of random access memory. So in that scenario, both are random in nature. Fine. In the storage type, that is different. So one is called as volatile. This RAM is called as volatile memory, and this is called as non-volatile memory, means permanent memory, non-volatile. Okay, volatile means it is based on the power supply. When the supply is off, data will be lost. So this is non-volatile memory. There are several types in this. Fine, that's about the primary. We shall now discuss how a particular simple RAM memory can be present. You can write that point. Note, both RAM and ROM are random in accessing. That is, the time taken to access any memory location is same. That is called as random access memory. Okay, fine. So that is the meaning of this random. The time taken to access any of the memory location is same. Fine. Now let's consider the next point. What is the meaning of memory? I am elaborating the discussion of address bus now. Fine. Let us see what is the meaning of memory. So this memory, what I am talking about is primary, not secondary. What is memory? Memory can be said as group of some registers. So memory can be considered as group of registers. Memory is a group of registers. So how do I write this? Memory is a group of registers. Okay. Memory is said to be a group of some registers. I am naming these registers as, like, it is some R0, R1, R2, so on, etc. some Rn minus 1, because I am starting from 0. Fine. So these are some group of registers. How to understand this register? See, memory is a group of registers, and a register is a group of flip-flops. So let us take this flip-flop. Register is simply group of flip-flops. So here, if I consider register is a group of flip-flop, and a flip-flop is a memory cell which can store a bit. So one flip-flop can store one bit. This bit could be either 0 or 1. Very simple. We are discussing about primary memories, not like CDs or DVDs. We are discussing how memories are present in the IC form. Okay. So memory is a group of registers. A register is a group of flip-flops. A flip-flop is again some memory cell which can store a bit, that could be either 0 or 1. So normally what happens is, each flip-flop can hold one bit. It is something like a bistable multivibrator. It can have two states, 0 or 1. Fine, based on the triggering of it. Now observe carefully. For example, based on the value that is present inside it. So now I am considering like this. Say, each flip-flop may have one bit. Say for example 0, 1, 1, 1, 1, 0, 0, 1. So every register, let us say it has got 8 flip-flops, so 8 bits can be accommodated. 8 bits means how much value is that? It is 1 byte. So we can say that one register can hold 8 bits here, so 1 byte of data is present in the memory. So this register is also called as memory location or address location, or are same. So memory contains some registers, register contains some flip-flops, and flip-flop contains some bit, that is 0 or 1. Assume that all the registers can hold 8 bits each. So this memory is represented in the form of bytes. So the standard unit of memory is said to be in terms of bytes. Okay, fine. Okay. So here, if there is one register, capacity is 1 byte. If there are n registers, capacity is n bytes. Okay, let us say 100 registers are there, 100 bytes. Some 2 power 10 registers are there, that many bytes, so on, etc. So here, in this case, what is the word length? What is the standard word length of memory? 8 bits. Okay, so how many bits it can have in one register is word length of that particular memory. If each register has got only 4 bits, the word length is 4 bits. If it has got 16 bits, word length is 16 bits. That may be changed based on the requirement. Okay, fine. Now here, I want to name these registers. I want to give some name to the registers. How to understand this? I want to allocate some addresses to them. How to take that addresses? Let us consider like this. Say here I am taking addresses. If there is only one address, see, memory is a complex concept. Internally there are complex logic circuits. Let us not worry. We will discuss whichever is required for us. Okay, let us not worry the internal design. We are concerned with how the memory is connected to the processor to solve the problems. So let me take in a simpler way. For example, I have got one address line A0, right? So one address line can support how many bits? 1 bit, that is 0 or 1. It means 0 is one address, 1 is another address. Okay, if there are two addresses, there can be possibility of two registers which can be connected to this one wire. It means this is R0, this one is R1, two registers. So the first register, say it is connected through some NOT gate and the second register is directly connected. Okay, fine. Now observe carefully. For example, if I am considering this is the address line, this as an address line, okay, say this is the address line. Whenever, see, each register has got 8 bits, that is common. If the address is 0 on this particular line, it's a NOT gate, it becomes 1. So first register is selected. If the address is 1, then this will be 0, second register will be selected. So for 0 address, the first one is selected. For 1 address, second one is selected. It means that if there is one address line, how many addresses are possible? 2 addresses. So how many registers are possible? 2 registers. So how much capacity of memory can be possible? 2 bytes. Here I am taking the default size of each data in the memory is 8 bits or 1 byte. So 2 registers are possible, so 2 bytes. It's a game. Now inside the memory there is some kind of decoding logic, such that the register is selected. So we don't bother about this decoding logic. Okay, so don't worry about the decoding logic here. Let me just okay, you don't worry about the decoding logic here. There is some sort of decoding logic. This is decoding logic such that register is selected. So very simple now. If there is only one address line, 2 registers, so 2 bytes is possible. If there are 2 address lines, 4 bytes are possible. 3 address lines, 8 bytes are possible. If it is 4 address lines, 16 bytes are possible. 5 address lines, how much it is? 32 bytes are possible. 6 address lines, 64 bytes are possible. 7 address lines, 128 bytes are possible. 8 address lines, 256 bytes are possible. And 9 address lines, it is 512 bytes are possible. And 10 address lines, it is 1024 bytes possible. This is what we call it as 1 kilobyte of memory. So based on this, you may have some problems. There are some junctions here. So let us take some junctions. For example, say to understand clearly, I am considering like this. Okay. So let us consider like this. 2 power 10 is called as 1 kilobyte or 1 KB. 2 power 20, that many addresses, 1 mega addresses, so 1 megabyte, 1 MB. 2 power 30, 1 gigabyte or 1 GB. 2 power 40, 1 terabyte or 1 TB. So let us now solve some questions based on this 1 terabyte. So you'll have some junctions given here. You'll have some junctions, like you'll be given some number of address lines. You're asked to find out how much capacity is stored, or you'll be given memory. You have to find out the address lines. So this is the discussion how we have gone for the memory. So this notation, you'll be having some problems on this. So you should know what is this 2 power 10, what is 2 power 20, what is 2 power 30, and what is 2 power 40. If it is 2 power 50, we call it as petabyte. It's not required. 1 petabyte. Understood. Let us solve some questions based on this. Okay, let us solve some basic questions based on this memory concept. Right. A processor has 16 address lines, or let us say I am taking other value, not 16. A processor has 25 address lines. 25 address lines. Find the maximum memory that can be connected. Find the maximum memory that can be connected. Very simple. What is the relation? 2 power n is equals to n. Fine. So how many address lines are given? 25. Therefore 2 power 25 can be written as 2 power 5 into 2 power 20. By default, we are considering each memory register has got 8 bits. So what is the value? 2 power 5 is 32, 2 power 20 is 1 megabyte. Therefore, the maximum memory possible is 32 megabytes. That is how we can solve the data. It is very simple, just substitution value. Let us take the other problem. Say maximum memory is given. Maximum memory is given to you. Say it is 512 terabytes. Now you are asked to find how many address lines are present for the microprocessor. How many address lines are for microprocessor? Reverse, very easy. 2 power n is given as 512 terabytes. 512 is 2 power 9. 1 terabyte is 2 power 40. Therefore, 2 power 49 is equal to 2 power n. The value of n is equals to 49. This is how you have to find out the memory, or you have to find out the address lines. In the third case, sometimes you will be given in other way, like for example, say the memory that is connected to a processor is 100 GB. Find the minimum address lines required. Very simple. Now look at this. Is the capacity 100 GB? GB means it will be in the range of 30, that is confirmed. Is 100 a power of 2? No. What is the exact power of 2 before and after this? Before it is 64 GB. Okay, 64 GB. Other one is 128 GB. For 64 GB, how many address lines are required? GB means 30, 64 means 6. For this one, how many are required? 37. Here, if you consider 36 lines only, the maximum possibility is 64 GB. Right. But the given target for us, whichever is here, this target is more than 64 GB but less than 128 GB. Means above 36 till above 64 GB till 128 GB, definitely we require the number of lines as 37 only. For example, you are watching cricket. Okay. Current over is 3.4 over. Tell me, 3.4 over is third over or fourth over? Anything that crosses 3, it comes under fourth over only. The same way, here above 64 GB till 128 GB, the minimum lines required are 37 only. Because if you take 36, it can address only 64 GB. Above 64 GB till 128, definitely it required 37. That is why the question has been asked as what is the minimum number of address lines. So answer is how much? 37. That is how we can solve the problem. I hope you have understood what this memory is. Clear? We shall continue the further topic.